And then I can see if there's any questions on Shor's algorithm or Hamiltonian simulation or any of the other stuff we've been doing.
So I was looking at, oh, Dan.
Yeah.
I was looking at the advanced question from the tutorial last night on Hamiltonian simulation, and like this is where we kind of cut our we cut our system up into like different boxes and we measure the positioning for those.
Right.
And I was thinking like you can kind of simulate this some way by picking like if you allow yourself like different functions inside the boxes, or like each kind of box to measure to be a different basis state, then you can kind of potentially optimize this for different problems. Have people looked into that, or?
Yeah, sort of. So when people talk about, for instance, simulating chemistry, so you have some chemical interactions. Frequently, the basis that they use actually to represent the states are some sort of orbital basis.
Yeah.
I mean, obviously, for hydrogen atom, you could use the hydrogen atom orbitals. For molecules, you want to use some other kinds of orbitals that spread out between the things.
Yeah.
I don't know exactly what orbitals they're actually talking about using.
Yeah.
But certainly, it's not a straightforward particle. Electron 1 is here, electron 2 is here.
Okay.
Basis. So yeah, that's definitely something people do.
Okay.
Yeah, in fact, you can spend in any basis you like. And the idea would be to pick one in which the interactions are pretty nice.
Yep.
But also, ideally, one in which particles tend to be more localized, I guess, so that you don't have. Let me think. What is the property that you would want? I mean, you want the Hamiltonian to be kind of close to diagonal, I think, in that basis, right? If you can diagonalize it perfectly, then you've solved the problem. Presumably, you're not going to do that, but if it's mostly diagonal with only a small perturbation, then all this trotterization stuff will work a lot better because you have only this small correction that you're applying.
And is it like, I mean, one of the things I realized when I was thinking about this is it's kind of important to make sure that when you're choosing your basis that you don't just get one that's kind of like close to the identity, but one that like also the off diagonal elements can be easily modeled by like unitaries that you can access from your quantum computation, right? Like,
yeah, that's right. So usually you want the interaction, the off diagonal part of the interaction, to be kind of local in the basis, in the sense that it only each term, it's a sum of terms, each of which only involves a few basis states,
right. Okay.
or the interaction of a few basis states. Because anything else can be hard to then implement the actual term in the Hamiltonian. Maybe it's worth mentioning that in the past couple of years, there's actually been substantial progress on Hamiltonian simulation algorithms, and kind of the way you did it in the tutorial was kind of the simplest, oldest way of doing it. But people have come up with ways that are better in various ways, more efficient, lower error rates, stuff like that.
When you talk about like quantum simulation, like doing things that would be kind of efficient in terms of quantum gates, is this a principle that ties back into when people talk about tensor networks and matrix product states as well?
I don't think there's really much overlap between the techniques. I mean, the stuff on matrix product states and tensor networks is attempts to do a classical simulation of a quantum system. And I'm not aware, actually, of too much overlap with these quantum simulation methods. Although, in principle, I mean, certainly some similar ideas are there. The main thing is that if there's a good classical technique for doing it, you don't really need the quantum technique. But other than that. OK, so are there other questions, actually? OK, so in that case, let's move on to Grover's algorithm. So as I say, Grover's algorithm is an unstructured search problem. So let me define that. So this is an oracle problem. And the oracle is going to take the numbers from input a 0 to n minus 1, say, or 1 to n if you prefer, and output a bit. And the goal is to find if there exists some input such that the output for that input is 1. Or more generally, to find x0. Okay. So this x0, or just any input that has this property that the output is 1, is usually called a marked element. So the idea is you imagine having some long list of big N things, and some of them are special, are marked. And if you look at a particular, one example that people have given of this type of Oracle problem is, this analogy is maybe no longer comprehensible, but the reverse phone book lookup. So phone books barely exist anymore, but probably you guys remember them from your distant childhood. They were long lists where you had a name and a phone number, and they were arranged alphabetically. I have to come up with a new analogy, I guess. So the question is, suppose you have the phone number and you want to find out who it belongs to. Right? This is kind of hard to do because you look through this long list. It's arranged alphabetically. You look, say, is that the right phone number? Is that the right phone number? Is that the right phone number? Until you finally find the right one. So the point is that it fits into this framework because given the input, x, you can easily just look up the name, right? The x is the name, and you look it up and you see, oh, is this the phone number I'm looking for? So that's the bit, yes or no. Okay. But as you can see from this analysis, classically at least, this is a very hard problem to solve. And more generally, so the phone book lookup is kind of silly for a couple of reasons, not least because it's obsolete. But the unstructured search problem is also kind of a nice abstraction of NP-complete problems. And in that case, the oracle is the verifier function, and the input is a potential witness. So the idea is you may maybe have satisfiability instance. So you have some Boolean formula, and you can say, okay, let me guess a possible satisfying assignment. So I'll take all those variables and assign true or false to them, and then I can try it out. And that's like plugging an input, the potential satisfying assignment, into the oracle, the verifier, and then you'll get an output which is yes, this assignment works, or no, it doesn't, which is the output of the value of the Boolean formula, true or false. And so then the marked elements are the valid witnesses. And the unmarked elements are the ones that are not valid. And so then solving that satisfiability instance is equivalent, well, not equivalent exactly, but it's sufficient to solve this oracle search problem. If there exists a marked element, then we know it's satisfiable. Yeah?
So when you talk about this being NP complete, we're talking about like the order, like the size of lists, right? Or is
no. This problem is not an NP complete problem. It's an oracle problem.
Right.
I'm saying it's a model for NP complete problems.
Okay.
And so yeah, so in this case, N is the set of possible inputs.
Right.
So in the example of satisfiability, big N here, so there's little n variables,
Yep.
x1 through x little n. And so there's 2 to the little n possible assignments.
Right.
And so big N is 2 to the little n.
Okay. Sure.
Okay? That was actually what you were asking, I think, right?
Yeah.
Okay. Yeah.
Why complete?
Yeah. So okay, it's true. It's a good abstraction potentially for any NP problem. So the reason specifically NP complete problems. So how does this differ from an NP problem? Well, it differs because this oracle is an oracle. It's a black box. We don't know what goes on inside it. So in principle, given any NP problem, sure, you can take the verifier and treat it as an oracle, and then try to solve it this way. But the thing is, there might be a much better way to do it by taking advantage of some structure in the problem. So for instance, if that's a 1 satisfiability instance, well, yeah, sure, you can still do this. But as we discussed, that's really a kind of trivial problem to solve, even though this oracle problem is not. Okay? Because you say, well, actually, I don't have to take all of the assignments of the variables at once. I can look at the variables one by one, because the clauses are only treating them one by one. Okay? So the reason specifically I say NP-complete problems is because we believe that for NP-complete problems, while there may be structure, it's not really structure we can take advantage of in solving the problem. Whereas for NP-incomplete problems, well, presumably there is some structure, which may or may not be enough for us to solve the problem. In the case of factoring, it's enough for us to solve it quantumly, but maybe not classically, for instance. Yeah. So let me say that basically, search is a method to solve many, many problems. And this is a search where we don't really learn anything from our queries. So you can also have searches where you can make a query, and even if it doesn't give you the answer that you want, it tells you a bit more about the structure of the problem. And then you can take advantage of that to adaptively make the next query that depends on the outcome of the first one, and so on. And of course, you can make adaptive queries here, but it doesn't really help, because knowing the value of one input, x, knowing what O of x is, doesn't really help you learn anything about what O of y might be for any other y. Okay, so the classical result here, as maybe you gathered from the discussion before, is that there's a lower bound on the query complexity. And that lower bound is omega of n. So omega notation is just like big O notation, except the inequality is greater than or equal to. So omega is used for lower bounds. O is used for upper bounds. So when we say, here's an algorithm that solves the problem, that's an upper bound, because there might be a better algorithm that we haven't found. But we know that the best algorithm is at least that good. That's the upper bound on the query complexity or the running time or whatever. In this case, so there's a lower bound on the query complexity, which is you basically have to try a large fraction of everything. And this includes the randomized query complexity, not just the deterministic one. You basically have to try a large fraction of all the inputs before you can get the answer. Of course, there's also an upper bound, which is O of n, which is try everything. Okay, so in fact, we say it's theta of n. So that's the case where you have the matching upper and lower bounds. And so in the quantum case, it turns out that the query complexity is made of square root n. So there's a lower bound that says that you need at least square root of n queries, order square, roughly square root of n queries up to constants. And then there's actually an algorithm that takes O square root of n queries. That's Grover's algorithm. Okay, and maybe the intuition here that you can think of, which, I mean, we'll talk about exactly how this algorithm works in a little bit. But in the classical case, like I said, there's no structure here. You can't learn from one query anything about the values of other inputs. So the only thing you learn is that the one you tried didn't work. Or maybe it did work and then you're done. But the point is that if there's only one marked element in this whole big list of n things, then basically you can't do anything better than just try stuff at random, just so long as you don't repeat yourself. And so the probability of success per query is 1 over n, right? And so clearly you need about n of those queries before you get lucky and happen to find one that works. Now in the quantum case, you can kind of do the same thing, but you can query in superposition. And now instead of having a probability of success 1 over n, you have an amplitude of 1 over square root of n being the right query. And then Grover's algorithm kind of gives you a way of having the amplitudes add up coherently. And so by doing a little rotation of giving you extra square root of n of the correct amplitude every time, you can have those build up after about square root of n queries into something that's order 1 amplitude of success. Okay?
So if you're like doing any kind of stuff work in databases, you don't work with unstructured lists.
Mm-hmm.
But this would be useful in terms of like sorting as well, yeah?
Let me think. So there's some work on quantum algorithms for sorting. I don't remember what the results are. Sorting is a little more subtle in various ways. But I think it may use some Grover subroutines, so I'm not certain. Now, if the list is already sorted, then you can search it much more quickly than this, right? Then it's like log n time. To an alphabetical list, you say, well, OK, somewhere in I know it starts with C, so it's going to be somewhere in the top half probably. So I'll look somewhere until I find where the C's start, and then kind of narrow down within the C's. And that takes, you can again do this divide binary search and get it in log n time. Assuming anyway, there's data structure issues of making that work well. But if you have an unsorted, but even if you have a sorted list, but you're interested in something that's not what you sorted for, okay, so you're interested in some more complicated property, like the reverse phone lookup, then this starts to become relevant again. And as I said, it's also relevant when you're doing things like trying to solve NP-complete problems, and you want to try to search through all the possible witnesses. So that's something where you just try a whole bunch of things without, if there's no structure that you can take advantage of, you're just trying a whole bunch of things and not really learning anything except that what you tried didn't work. And Grover's algorithm can improve that, right? And remember, I mentioned yesterday, this, while it's not an exponential speedup, can still be quite big in real terms. I mean, if the original list of things is 10 to the 10th elements, then this is taking it down to about 10 to the 5th queries, which is something that's kind of much more reasonable to do. So it's a 10 to the 5th factor speedup is pretty good, even if it's not exponential. So what else is this useful for? Well, so another case where people actually do kind of exhaustive searches. I told you about how factoring is good for breaking RSA. But there are, as I mentioned, other crypto systems like AES, which are not so easily broken. by quantum computers. And one approach that people can try to do that is to try a large number of possible keys in order to break them. And sometimes they can be a little more sophisticated with which keys they try. But Grover's algorithm lets you speed that search up as well. So kind of in order to get equivalent security against exhaustive search classically versus exhaustive search quantumly, you would need to make the key twice as long because twice as long is compensating for the square root. 2 to the n versus 2 to the n over 2. Other examples? Yeah. So I mean, there are plenty of other applications where you're doing some search. Sometimes it's not really even an exponential search. It might just be a relatively small search. And nevertheless, Grover's algorithm can reduce the number of queries. So that's the case where it's a medium-sized search maybe, and each query could be expensive, for instance. And then there's kind of some things maybe which are not immediately evident that they're search. And there's some examples of how to use Grover's algorithm on the homework that you'll be getting. Yeah?
I have a question about breaking RSA.
OK.
Like, let's say that I have, what?
Cut the cameras.
Yeah, cut the cameras. Let's say I have a computer that, let's say, I have my computer, and I've protected something with RSA.
Right.
And somebody wants to try and break that. But my computer is a classical computer.
Yes.
Is there a way that they can do that? Because it seems like in order
Sure.
to do that, they have to be able to, like, query something on my computer which is not protected against decoherence, and then like interfere stuff back together.
Sorry. OK. So first of all, RSA is mostly used in communications.
Right.
The advantage of a public key thing is that the person encrypting doesn't need to know it. But yeah, suppose it's a classical communications. Alice is sending a classical message to Bob. But Eve can intercept that. And if you think back through what I showed you the past couple of days, what Eve is going to do is she's going to say, OK, I have this public key. Part of the public key is this number n. I want to factor n. She doesn't even really care what the message is for that, just the public key. And then she does this classical pre-processing and says, OK, in order to, I want to find this element x that has even order, and x to the r over 2 is not minus 1 mod n. So how do I do that? Well, let me pick some random x, and I'll run a little quantum algorithm to find the order of x.
Right, but she does entirely on her own.
Yeah, and that's entirely on her computer. She's not taking any input. She doesn't have to check anything.
Okay.
So let me give a different example, which is a little bit closer to what you want. Passwords on a computer are usually protected by some sort of hash function. So that's not a public key system. That's a kind of different thing where when you get there, you sit down, you type in your password, and the computer runs it through some complicated function that scrambles it up into some other number, and it stores the scrambled number in its memory. Okay, and then, so it tries to match this scrambled number with the one that it's stored. Okay, so when people break into computers, one thing they like to do is they like to steal this password file, the encrypted password file, and run password crack programs on it to try to find out people's passwords. Now, some people have insecure passwords. They use their dog's name or something. Or password, you don't even need a password cracking program. Yeah. But so they use if your password is just a word from the dictionary, a standard dictionary, including a dictionary of names, then these password crack programs will run through all the words in the dictionary. And nowadays they run through combinations of words and distortions of words and stuff like that too. So if it's too close to a word in the dictionary, it'll run through this long list of possibilities, and eventually it'll match it to the insecure password. And so the point is that this function is kind of publicly known as part of the operating system. Everybody knows how the things are scrambled up. There's no secret there. But the problem is going the other way. It's what's called a one-way function. Going the other way is very hard. So they try a bunch of inputs to try to get this output. Now that's something that you can speed up with Grover's algorithm, because the function, again, is publicly known. So you can convert it into a quantum implementation of this function and run it on a quantum computer to make a quantum oracle. Okay, that says, given this input, does the output match?
And in order to do that, they have to have this password file. They can't.
Well,
They can't
otherwise,
do
without the
that.
password file, they have no way of knowing whether it matches or not.
Right.
Okay.
It's not like they're actually, putting in a superposition of queries to the actual computer that they're trying to break into.
That's right.
And that
Now, you could imagine a different situation where they haven't gotten the password file, and so instead they're trying to log on to the computer, right? And if they succeed in logging on, then they know they got the right password.
Right.
Okay. Now that's something that would be much, much harder to do,
Right.
and probably you couldn't do with Grover's algorithm. You couldn't do it in real life either, because usually the computer will time out
Yeah.
if you have too many failed passwords.
Right.
Although
You
apparently,
do them all simultaneously.
was it the iCloud didn't time out when you tried failed passwords, and this may have been the insecurity that let people hack in and get stuff.
Because
But
they just tried 10 million passwords.
yes, that's a possibility. Anyway, the point is that's something that even if it didn't time out, because the other computer is classical, you can't really make the oracle easily quantum.
So you have to first get the password file by
That's right.
normal deception.
That's right. Yeah.
I mean,
Yeah.
if you go to like 50% of banks store their passwords in plain text, so you don't even need to go out. You don't even need to worry about your
Did they
quantum.
really?
Yeah.
Let's
You
go
want
back.
you want to see like insecurities. You
Camera
should
stop.
see-
Yeah, there's a lot of real-world systems that are insecure,
Yeah.
and talking about doing all this complicated cryptography stuff to protect things is only relevant if you've handled some of the more basic security stuff.
It's like putting a lock on the door, right?
Yeah, that's right. Yeah. I mean, maybe a better analogy is cryptography is the lock on the door, but if you have your ground floor window wide open, maybe it doesn't really matter.
Yeah.
Okay, but that's a whole separate realm of security rather than cryptography.
Right.
The goal of cryptography is to kind of make the basic mathematical primitives that at least have the possibility of making things secure. And of course, quantum is even a step beyond that. So, but I should probably get on to talking about Grover's algorithm specifically. Okay, so but before I do that, people have the general overview of what we're trying to do here. They understand the problem. Okay. Okay, so I want to first look at the special case where we have just one marked element. X0. Okay, so because this problem has no structure, there's only two classes of things we have to worry about, right? There's the marked elements and the unmarked elements. And we have no reason to treat any of the unmarked elements differently from each other. So, so what we're going to do is we're going to work in a two-dimensional subspace. Which is spanned by two basis elements. So one of them is just x0. And the other, and I'll call that S, the other one is t. And that's the sum over x not equal to x0 of x. Okay, so it's the sum over all the unmarked elements. Okay? And every state, well, at various points in the algorithm, I'll be getting back to the subspace. And the states that I'll get at that point are always some superposition of S and T. Okay, so let me work on this picture. So we have S. No, this one S, and this one T. And somewhere in the middle, I'll have psi here. So, so what can we do to move around in this subspace? What operations do we have that will preserve this subspace? Well, one thing we can do is we can make an oracle call. And using this phase kickback trick I showed you before, I can convert a single oracle call into a phase oracle call. So what does it do? So you can call it -1 to the O. And so if we have psi is equal to alpha S plus beta T, then -1 to the O applied to psi will, it'll give us a sign of, I guess, -1 for S and +1 for T. So this will be minus alpha S plus beta T. And so what is that going to be in this picture? Well, the T component of psi remains the same, and the S component gets reflected over the T axis. So this is going to be down here, -1 to the O psi. OK? Make sense so far? OK. So what else can we do? We can make the element U, which is S plus T, which is just the sum over all x of x, right? Just the sum over everything. So this is an element of this subspace, and it's easy to make because it's the Hadamard transform applied to the all zeros state. Okay, so that's good. And then using this, we can actually do a little bit more. So what do we have so far? We have the ability to make some particular state, which is going to be close to T. And we have the ability to reflect over this T axis. But it turns out we can also reflect over this state U, here, which I'll draw in here. So how do we do that? Well, we can reflect over the all zeros state with the following operation. And, oh yeah, sorry, I did do that. And it'll take anything else to minus x. Okay? So that's a perfectly valid operation. This is a quantum gate. It doesn't use the oracle, so we don't really care about how many gates it takes. But in fact, it takes, when you have n qubits here, it takes some polynomial in n gates. Probably you can do it in linear if you want, although that might not be the most space efficient. OK, so this gate here is a reflection over the all zero state. And the all zero state is related to the U state, which is in our subspace via the Hadamard transform. So what we can do is we can make a reflection over U. And what am I going to call that? -1 to the U. And what is that going to be? Well, what I'm going to do is I'm going to rotate U back to all zeros, or rotate that way, and then do F0, reflection over all zeros, and then rotate back. OK? And so what this does is reflects over U. Let's see. Yeah, OK. So let me be a little more careful. So so I have a Blackboard issue here. Okay, so what I'm going to do is I'm going to alternate between these two reflections. So let me call this operation G. First, we'll do the reflection -1 to the O, and then we'll do the reflection -1 to the U. That's an O, not a 0. So the reflection over O I've already drawn here. We take psi, reflect it down to here. So let's see. So this angle, here, maybe I can use colors. This angle here, I'm going to call phi. And so this angle here is also phi. And then let's let this angle here be theta. And so now, so if I do the first reflect over t, here I have this state. Now I'm going to reflect this thing over u. So it's an angle phi plus theta away. So we should get, here we should get something that's a total of phi plus theta. And then we get this state up here, which is G applied to psi. Okay? And so you see what's happened here is that we started with something that has an angle phi away from the t-axis. And now we have something that's an angle phi plus 2 theta away. Okay? And so you see that if we start out with u, and then we do roughly 1 over 2 theta. If we do g roughly 1 over 2 theta times, then we'll end up with something that's pretty close to the s axis. And s is the answer. So if we measure at this point, well, with high probability, we'll get the marked element. Okay? And that's Grover's algorithm.
How can you prepare your system in a state finally equal to theta?
Sorry. So the state U is a state that we can easily make because it's just the Hadamard transform on all zeros.
Yep.
Okay. And so I'll write down the exact algorithm in a moment. But that's what we're going to start with, and then we're going to do G many times. But let me first figure out what theta is.
Okay.
Okay. So theta is the angle between u, which is, and so now I'm going to, all of a sudden I care about normalization because I'm about to take the inner product and I need to know the exact value. So normalized u is going to be, well, okay. So it's really, let's put the normalization here. So it's 1 over square root of nu, because u is sum over n different values. And t, which is a sum over n minus 1 different values. So the normalization should be 1 over square root of n minus 1 times t. And so I can find that by taking the inner product. So I have, these are now unit vectors. So the dot product between them is 1 times cosine theta. And what's the inner product? Well, that's 1 over root n minus 1, the inner product of u and t. Now, u is the sum over everything. T is the sum over all the unmarked things. The inner product between the two basis states is only the same when they match. So when do they match? They match on the n minus 1 unmarked items. So this is n minus 1 over root n minus 1, or a square root of n minus 1 over n. And of course, then you can find sine theta, square root of 1 minus this squared, and that's 1 over root n. Okay, so you see that when n is large, theta is going to be small, and theta is going to be about 1 over root n. And so doing 1 over theta things is order root n. So that's where the root n is coming from. OK, everyone with me so far? OK, so let's write down the actual algorithm. So step 1, we initialize to size 0 to be u. So that's, and we can do that by taking the Hadamard transform on the all 0 state. And so at this point, we have an angle with t, which is going to be called phi 0, and that's equal to theta, which I just calculated. So next, we have a repeated step. And so in this step, we apply g, which, just to write it here again, is minus 1 to the u, minus 1 to the o. We apply it some number of times, m times. And so each application here, G, uses one oracle call. And so then after the kth application, we have the state psi sub k, which is g psi sub k minus 1 by definition. And the angle phi sub k, which is, by the argument over there, is phi sub k minus 1 plus 2 times theta. And then at the end, after doing this, we measure to get a candidate value x0. And then we could just verify to see that we really did. And that uses one more oracle call. We did get it to pack the markdown. Okay? Okay, so to be a little bit more explicit at this step 2, we can write down an explicit value for psi k, right? We know it's in this 2-dimensional subspace, and we know its angle with t is this phi sub k. So phi sub k obviously is going to be 2k plus 1 times theta, since it starts as theta and we add 2 theta every time. And so psi sub k is then going to be cos of 2k plus 1 theta t plus sine of 2k plus 1 theta s. And so we should end by letting m be, well, m has to be an integer, obviously, but we want it to be something that's as close as possible to this being equal to 1. So that saying 2k plus 1 theta should be pi over 2. Sorry, 2m plus 1 theta should be about pi over 2. So it's saying that m is going to be about pi over 4 times it's pi over 4 times 1 over square root of n, which is, since theta is about 1 over square root of n. Oh yeah, so there is the inverse sign. Anyway, whatever. This is certainly the correct asymptotic value for small and there's slight correction.
You can, even if you have small n, you can kind of rotate many times.
1 over theta, 1 over theta.
Even if you have small n, you can like rotate many times to kind of get it around. Kind of, like if as you rotate more times, you may be able to get it closer and closer.
Yeah, there's not really any point in doing that.
If n is small, then you can just try it.
So there's a couple of things you can do. So first of all, I mean, you'd like to be as close to 1 as possible, but it's not actually that important, okay? Because if you try it and it doesn't work, you can try again.
Yeah.
So all you really need is that the probability of success that this sign is kind of order 1. So if it's a half, that's fine. You just do it twice.
Okay.
If it's a tenth, you do it 10 times. So it's not worth going around many times in an effort to solve that problem. But actually, it turns out, because we know exactly what these angles are, you can fiddle with this algorithm to rotate by different amounts other than 2 theta. And because you can tell exactly what these numbers are, you know exactly how much. And in fact, you can, by fiddling with numbers, you can make it exactly hit S if you want to. So that's not actually a very important trick, because as I said, it's not that important to get that close. But the other thing, of course, is that the case where you know that there's exactly one element is a little bit of an artificial one. And so we'll get to multiple elements in a moment.
You can get kind of the speed up by, rather than just using u, by using like, if I rotate one qubit like a bit beyond u, and then I can go, then rotate the second one around the first one to go even further, right?
No, sorry, I didn't quite understand what you're saying, but one thing to remember is that the oracle looks at the whole input. It's not looking at it bit by bit.
Right.
So we can't apply this at all unless we're unless we're letting the register run over actually all the values of the input and kind of treating them collectively.
Yeah, right. Sorry, that doesn't work.
Okay. But one thing maybe that's worth noting about the solution is that that if we run it too long, I mean, so if you pick m to be about this value, then you'll get something that has probability of success that's close to 1. If you pick it less than that, obviously the probability of success will be less than 1. But because it's trigonometric functions here, if you do it more than that, the probability of success is also going to be less than 1. So if you run it too long, you might think that more oracle calls are going to be better, but no, they're not. It's not just you're not getting any more value, it's actually getting worse again. Of course, if you run it long enough, it'll come back around and it'll be high probability of success again. Okay, so you have to stop at the right time. Okay, so any more questions about the one marked element case for Grover's algorithm?
So we choose m to be pi over 4 root n?
Yeah, we want it to be an integer that's near this. So yeah, so something like that. Okay. Okay, so, sorry, yeah.
Regardless of theta?
No, yeah, so that I put in the value of theta. So actually what we want that 2m plus 1 theta should be, here, let me do the actual calculations. 2m plus 1 theta should be pi over 4. Theta is a fixed value given by n, which we calculate over there, right? So theta is actually inverse sine of 1 over root n. So this is saying that we want m, so this is pi over 2. So we want m to be pi over 2, 1 over theta, minus 1 over 2. And then plugging in, and then ignoring this and plugging in theta is about 1 over root n, we get this.
Thank you.
Okay? Other questions? Okay, so then let's move on to the case where there's more marked elements. So in particular, suppose we have T marked elements. So what we're going to do is we're going to run the same algorithm, but we're going to run it a different number of times. Use different values m. So when there's T marked elements, again, we want to treat the marked and the unmarked. We want to treat all the unmarked elements symmetrically. We also, now there's multiple marked elements, we want to treat them symmetrically as well. So what we're going to do is we're going to let S be the sum over marked elements of the marked elements, and T is going to be the sum over the unmarked elements. Okay? And it's still the case that U is S plus T is the sum over everything. Okay? So it's still the case that when we run this algorithm, we initialize to U, we're still starting in the appropriate subspace. But the thing that's different now, and we can do all the other steps, right? We can do, so the minus 1 to the O is still giving a minus sign to S and not to T. So it's still a reflection over T. And the minus 1 to the U is still a reflection over U, right? Because that didn't depend on the oracle at all. And so everything is the same. The only thing that's different is what theta is. So what's theta? Well, we do the same calculation. We take the inner product. We have cos theta is, again, 1 over root n. But now it's n minus t, because t is a sum over n minus t unmarked elements. And the inner product of u and t is going to be, this is n minus t again. So we get square root of n minus t over n. And sine theta is square root of 1 minus this squared, which is square root of t over n. Okay? So when we do that calculation up there, again, we should let m be about pi over 4 square root of n over t to get the kind of the high probability of success. Yeah.
If t is very large.
Sure. So if t is very large, so this thing is not small, then you should apply that more exact formula. This is applicable when t is much smaller than n.
Right. But also, if t is very large, then like I'm going to do this, I'm going to measure, I'm going to get a result, and I want that result to be, a string of bits that is in my, like, that does return.
Right.
Is marked.
That's right.
Now, I have an error, I have like a probability of getting any one of the marked strings should be the same. And somehow I'm going to have to limit, but at the same time, so that means like I'm going to return like a spread of values for this T.
Well, no, so if we do it once, we'll get some element. There's a high probability it's a marked element.
Right.
And actually, that's all our goal here, is just to get a marked element.
All right.
And in particular, we don't have any control over which one we get. So we get a marked element at random.
Right. We just, rather than like worrying about whether or not we got whether or not we had an error, we just go and check it.
That's right.
Right. Okay. Cool.
Yeah.
So what if I don't know what T is?
If you don't know what T is, yeah, that's a catch. But before I go on to address that, are there other questions about the case where we do know what T is? Yeah.
So the problem is you find one marked element. What if you want to find all marked elements?
Yeah, so if you want to find all marked elements, then this is not quite as helpful. So, okay, so first of all, in the case where T is really, really large, like it's n/4, so obviously that's a case where finding a marked element is already not very hard classically, because you just try random stuff. You have a 1/4 chance of getting it. But even then, actually, Grover's algorithm offers a speed up if the oracle calls are very expensive. You can reduce the number of oracle calls. Now, if there's if there's like n/4 marked elements, then there's no hope for doing it with less than n/4 oracle calls, right? And so Grover's algorithm is not going to help that much in that case. Now, if there's 2 marked elements and you want to find both of them, then what you can do is you can run Grover's algorithm, get one of them at random, run it again. And if you want, you can even exclude the one that you've already found. That makes things a little more complicated, but doesn't fundamentally change it. And then you'll get the second one. Okay. So I guess I don't know for sure, but I think basically the complexity of finding all the marked elements is O of T times square root of n. And the reason is, okay, so finding one marked element is square root of O of square root of n over T. So you might think that finding T of them would be T times this. But I don't think that's correct, because finding the last one will still take O of square root of n. But that's just kind of a guess, and maybe there's something clever you can do that does get you somewhere in between those. So it's a question of whether it's square root of T times n or T times the square root of n. Somewhere in between those is certainly the right answer. OK. Other questions on the known number of marked elements? OK, so what do we do if we don't know how many elements are marked, which is kind of usually the case? Well, there's a couple of possibilities. So if we know that there's only a small number of marked elements, we can try running for different amounts of time. Right? We can try running it for pi over 4 square root of n time, see if we can find the marked element that way. If that doesn't work, try pi over 4 square root of n over 2 time, see if we can find a marked element that way. Then go up to however many marked elements we think there might be. Now, if T is reasonably large, say it's square root of n or something like that, then that's not a very appealing thing to do. But it turns out there's another trick we can do to kind of approximately figure out how many marked elements there are. So what is that? Well, suppose we run this for a different amount of time and plot the success probability, right? Forgetting we don't know, we have no idea how many marked elements there are. We're just going to run it for a different amount of time. But imagine doing it many, many times so that we can build up statistics on the success probability. Well, the success probability is going to go up and down, right? So some sine curve, or I guess probability would be sine squared. So let me draw that out. So let's actually draw the amplitude of success. So we start out with zero queries at well, actually not a 0 probability of success, but a very small probability of success. And it's going to go up to close to +1 and down to -1. It goes up like this, and then down like this, and up like this, and down like this, and so on. Okay? And what is the period of this function? Well, the period is pi times the square root of n over t, roughly, with those small corrections there. And so if we can find the period of this function, we know roughly what t is. And Shor's algorithm finds the periods of functions. So what are we going to do? So what we're going to do is we're going to have 2 registers. And in this first register, we initialize it to the sum. Sorry, I shouldn't use t there. What did I say? K. Sum over k. And then we're going to run. And this one gets going to be the sum over x. So we're starting Grover's algorithm in the normal way. And then we run this Grover iteration k times. So it's g to the power k. And so the number of times we run it is conditioned on this quantum register. And based on that, we run our Shor's algorithm. So what do? We have this superposition. Let's see. So you can measure this if you want. And then we want to do the Fourier transform up here to extract the period, and then we measure this. Okay? And what we're getting out here is telling us the period, and therefore telling us the number of solutions. Okay? And then you can run for the appropriate amount of time to actually extract one of the solutions. So this algorithm is called approximate counting. Because it counts the number of solutions to Grover's algorithm. Now, it doesn't give you an exact number, because you don't get the exact value of the period. You get something that's kind of close to the period, which is not an integer in general. And it turns out that the range of k that you run over is going to have a big impact in how exactly you can figure out the period. So if you run for really long k, many periods, then you can figure out the number very, very well. But if you only run for a few periods, then it's going to be much more fuzzy. And in general, if you run for a very long time, of course, that's many oracle calls. So you don't want to do that. So you want to run for a small number of oracle calls. If your goal is to solve Grover's problem, you run for a relatively small number of periods. You kind of figure out approximately what the answer is. And then you use the fact that you didn't really need to get 100% success probability in Grover's algorithm. You just needed a constant probability of success. And then you run it a few times and get an actual answer. OK? Yeah?
But didn't Shor's algorithm assume that a function was injective over a period?
Yes. Yeah, so it doesn't actually matter in this case. Yeah, so I agree that you should probably redo the analysis in this case to make sure it works. But the basic intuition is the same, which is that by doing this, you're getting something that's periodic in the amplitudes here that kind of get kicked back into this register here, and the Fourier transform will always extract anything that's periodic. I mean, it would even if you do get repeated values, it's kind of roughly going to work. The problem is that there'll be extra periods kind of associated with these kind of false repetitions, which will just confuse you. But again, we're not trying to be exact here. We're just trying to be approximate. And I don't think it even matters in this case because it really are the amplitudes going up and down is kind of the important thing.
You could try squaring it and finding the period which would be half the period you're looking for. Right?
Sorry, squaring it will still have the same period. Sine.
Sine squared half the period.
Oh, okay, I see. Yeah, but okay.
You still have the problem with like double.
Oh, still have the same.
But it's not.
Yeah, it's the,
Yeah, that's right. Right. But the other, more importantly, it. I mean, it's not easy to square because it's not something that you're not actually calculating success probability. It's coming out of the amplitude. So you could probably do it with 2 copies of this or something, but then you're using twice as many oracle calls, which is kind of going back to basically what you were doing before.
This is a discrete set as well, like of points. Like I know we've drawn this as like a continuous curve, but realistically, like you only ever get points along this.
That's
curve.
right.
And so I think also because like depending on whether or not n over t is rational or irrational, you could quite well find that none of those points actually repeat.
Yeah, I mean, but it's not. I mean, it's a different thing because you're not calculating a function here.
Yeah, right.
Right. So it's the amplitudes that are the important things anyway.
Right.
And it's true that those are not exactly repeating because it's actually a irrational number there. Yeah, basically, I agree that you should write it down carefully and do the analysis. But people have done that. So I'm not going to do it now.
Guess what, Alon? You got yourself a new homework assignment.
Okay, so we're over time, so let's end now. And the next week we'll be talking about other stuff. So we'll be talking about error correction, cryptography, and probably some information theory.